Hi everyone, I'm just going to be doing another Faraday's problem, and the problem is a rectangular coil with resistance R has n turns, each of length L and width W as shown in this figure. The coil moves into a uniform magnetic field B with constant velocity V, and it's asking what are the magnitude and direction of the induced current and the total magnetic force on the coil. And it breaks it up into three parts. And the first part is asking as it enters a magnetic field, and the second part is asking as it moves within the field, and the last part is asking as it leaves the magnetic field. So this is very similar to just any Faraday's problem, but in this case it's just asking for the force. If we can think about the Lorenz's force. So I'm just going to start by doing the first part, which is asking when this coil enters the magnetic field. And if I was to draw this to help you get a better idea of what this actually looks like, I'm going to draw it over here. Draw the same diagram that we have here. Our B field is going into the paper. So as it enters the magnetic field, our rectangular coil will look something along the lines of this. We have just a tiny part that's entering, and this will still be W, and then this will still be L, this whole length. So, just like any Faraday's problem, let's start by finding the flux. I will just use the general flux equation, which is just B times A, or the magnetic field times the area. But the integral form will get you the same answer too. So in this case, B will just be B, and then our area will just be, well, what area are we looking at? Well, the only area that that has flux in this case will just be this little strip that's feeling the magnetic field. So if I call this length X, and then this will still be W, our area will simply be X times W, if that makes any sense. So we're simply looking at this strip right here, and I'm going to call this little tiny length X, which is part of L. So X times W. This X is just a small part of L, which is entering the magnetic field. So now let's just find the EMF. It will simply just be the same formula, negative N turns times d flux dt. And this will just be negative N, and N is given to us, times d flux over dt, and flux is simply bxw. So, just like any other derivative, this would simply just be equal to negative NB, and when you take the derivative of x with respect to time, it will simply just turn to velocity. So again, this is from the dx over dt, which just means the change of position with respect to time, which is simply velocity. So now to find the induced current, and there will be some induced current going in a certain direction because its flux is changing. So the formula is simply V EMF divided by R. And in this case, we simply can just plug in our EMF, which is negative MB VW over R. And this will simply be our induced current. So now it's also asking for the total magnetic force. In this case, we are able to use a very general force equation which is simply just going to be IL cross with V, which is just the Lenz's force equation. But we also have to remember that it has n turns. So we can just multiply this whole thing by n. In this case, we're simply gonna have, well, since we know that force is a vector, we should figure out which direction this force is gonna be in first. So looking at my diagram, this diagram right here, the only part that will have induced current is this part. But the question is, in what direction? So I'm just going to draw the diagram right here. And all we're looking at is this little strip right here. I made it a little bit bigger so it's easier to see. And we know magnetic field's going in on this little strip. So what's going to happen is the induced magnetic field will go in the opposite direction to mitigate the change. So all that means is it will be going the opposite direction, or counterclockwise. So again, the induced magnetic field will be going out of the paper, or the induced current will be going counterclockwise. So let's just find the force from each component of this induced current. So let's first look at this top part of the strip. So we simply have to look at IL cross with B. So in this case, IL cross with B, which is going into the paper, will result in a force that's going downward. So the force from this will be going down. And then let's look at this one too. So IL cross with B will result in a force going up. So the force in this case will be going up. Now looking at the force in this component. So IL cross with B will result in a force going to the left. So now we can say that because these are going in the opposite direction, these forces will simply cancel each other out. And all we are left with is a force that's going to the left. So plugging in what we know for this force equation, we have N times I. I'm just going to take the magnitude to make things easier so we can get rid of the sign. So N, B, V, W over R times the length. And you shouldn't be confused. You can't just put the L here because this L is simply stating the part that has the force. In this case, we're just looking at this strip, this little bar right here, which is W, as seen in this diagram. So L, again, is not this L, but it's going to be W because it's the part that's feeling the force. So times W cross with B. So that means the force will simply be N squared, so N times N, times B squared, B times B, times V times W squared over R. Because it's a vector, we have to include the direction, which we figured out in this part right here. So this will simply be the force for part A, and also the direction. So now let's move on to part B, which is asking the same question, but it's asking as it moves within the field. So going back to part B, I'm just going to draw the diagram again to help you guys get a better idea. So we have a B field going into the paper. And then it's saying as it's moving in the magnetic field. So all that means it's fully submerged in the magnetic field. So this is relatively simple. Flux is not changing in this case, so that means there won't be an induced EMF and no induced current. So that means there will be no force. So again, when it's fully submerged, flux is not changing at all, which means there is no induced current. That means there's no induced B field. So all this means is no induced current and then no force because it's fully submerged in the B field. So moving on to part C, which is just asking as it leaves the field. So I'm just going to draw the diagram again to make it easier to see. If we have our X's, our B field, and in this time the rectangular coil is just leaving this B field. So again, we can apply the same methodology as we applied to part A. So in this case, the only part that we're interested in is simply going to be this section right here that's still in the B field. And if I use the same naming convention, this will just be X, and this side will simply be W. So finding the flux again, it will simply just be equal to B times A, or B times X times W for the area of the strip, which is the same from part A. So finding the EMF will be the same formula, negative N d phi over dt, or d flux over dt. And this will just be negative N times d over dt of bxw, or we'll get the same result as negative N dvw. Now finding the I induced, or the induced current, which is simply VMF over R, or negative M B E W over R. So now that we have the induced current, we can find the force. And using the same formula, N times IL crossed with B. In this case, now let's just figure out the direction of the induced current. So I'm just going to draw the same rectangular coil out here so we get a better idea what's going on. And we're looking at this section specifically. So what's going to happen is we're going to have an induced B field that is going in the same direction as the original B field to compensate the loss in flux. So the question is, which direction is the induced current going to be? Well, putting our thumb in the direction of the B field, we will get clockwise. So all that means is this will be the direction of our induced current. So again, let's figure out the direction of the forces from each of these parts. So if we do our right hand rule at IL cross with B for this side, we're going to get a force that's going down. So for this side, the force would be going down. And then for this side, IL cross with B, which is going into the board, it's going to be going this way to the left. And doing it for this side, IL cross the B will result in a force that's going up. So again, the same result happens. In this case, these two will cancel out, and all we are left with is the force going this way. So that will lead us to our answer. So it will be N times the I, which is MPV W over R, and I will just take the magnitude of that because we found the direction from this. So MPV W over R times the length. Again, we're looking at the length that is feeling the force, which will be the lift, times W cross the B. So the answer will simply be N squared B squared times V times W squared over R. And the B field again is going in this direction, to the left. So what ended up happening is we got the exact same answer from part A. We had the same magnitude and direction. So again, our answer for part A is the force is equal to N squared B squared V W squared over R, and it's going to the left. And part B, there's no induced current because flux is not changing. For C, we get the same direction and magnitude as part A.